recordings.
Oh, it's gonna be two.
Yeah, I screwed it up. I accidentally stopped recording instead of unpausing it. All right, so number nine. Let's go to number nine. All right, so we've got three vectors, v1, v2, v3. We're in section 4.3. And H is the space whose span is those three vectors. So all linear combinations of v1, v2, and v3. It can be verified that 4v1 plus 2v2 minus 3v3 equals 0. So you may have a slightly different, uh, what's called a dependence relation. This means these vectors depend on one another, like this. Use this information to find a basis for H. Okay? So, you may have different vectors, but I can do it but yours is probably similar, right?
Yeah.
So V1 is 7, negative 6, 1. V2 is 1, 9, negative 2. V3 is 10, negative 2, 0. And we are told that H is the set of all linear combinations of those three vectors, okay? So if you want to think about it, it's a set of, S times, S1 times V1 plus S2 times V2 plus S3 times V3, where the S sub i's are scalars. They're just weights, okay? Okay, the S1,
Yeah.
S2, and S3. This isn't supposed to be a dot there. It's supposed to be S1 times. Okay, so it says we know that there's a relation between these vectors. And my relation says 4v1 plus 2v2 minus 3v3 equals 0. Okay, so that means v1 is equal, well, let's do it in two steps. 4v1 equals negative 2v2 plus 3v3. In other words, v1 can be written in terms of v2 and v3. Okay, but we're gonna solve for v1. v1 is actually negative 1/2 v2 plus 3/4 v3. So v1 is a linear combination of v2 and v3. So one basis, there's numerous bases. A basis for H would be just to take v2 and v3, because v1 can be written in terms of v2 and v3. Does that make sense?
Yeah.
So you would just put these two in there. But 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 this also yields, you could solve and say, hey, 2v2 is equal to 3v3 minus 4v1. In other words, v2 is a linear combination of v3 and v1. So another basis for H would be just to use v1 and v3. See what I mean?
Yeah.
Because we don't need v2 if we've got v1 and v3. We don't need v1 if we've got v2 and v3. And guess what else? What would be the other basis that we could take that would work just fine?
So the
You,
V3.
yeah, v1, v2. See, here we didn't use v1. Here we didn't use v2. Here we don't use v3. Like, we only need two of them is the point, because there's this relationship between them. Like, you could solve for v3 in terms of the other two. See, that means V3 is kind of superfluous because V1 and V2 do all the work that V3 does. So any one of these three answers would be correct. Okay. Should we should we look at the next question? So this, you can use the go to the textbook, and read a little bit. But this next question, I'm sure it's the same for you as it is for me. Number 10 says determine if the following statement is true or false and justify the answer. Is that what yours says on number 10?
Yeah.
All right, so let's talk about this. It says a linearly independent set is a basis for H. So a linearly independent set in a subspace H. So these are going to be a set of linearly independent. That means there is no dependency relation. In other words, we're going to need all of them. But the question is a linearly independent set in a subspace H necessarily a basis? Well, remember, there are two things that a basis has to have, two properties. One property is that the basis has to be linearly independent. So that's good that we have that. We need that. But the other thing is that the basis has got to span H. There have to be enough vectors to build all of H. And so the reason this is false is because just because the set is linearly independent doesn't mean that it's enough to build H. It may not span H.
Okay.
So it's certainly not false because the set must be linearly dependent. No, no, no. A basis has to be linearly independent, but it's false because
Yeah.
the subspace spanned by the set must also coincide with H. In other words, you've got to build all of H from this linearly independent set, and we don't know that it's big enough to do that. All we know is that we have the linear independence. We don't know that we have the spanning property. Do you see what I mean?
Yeah. I do.
And the next question is similar. It says if a finite set of non-zero vectors spans a vector space, then some subset of S is a basis. And that's true because if it spans, it means it's got everything you need to build V. And a subset of S could be all of S because S is a subset of itself. Or if some of these vectors in S are dependent on the other ones, you can throw them away. And then a smaller subset of S would then still span V if you throw away the linearly dependent vectors. So this is true by the spanning set theorem. Like go back and look at the spanning set theorem. It says two things. It says if you have a linearly independent set, you can trim it down and get a basis for the space that it spans. It says if you have a spanning set, excuse me, if you have a linearly independent set, you can build it up until it spans the space. If you have a spanning set, then you can trim it down until it's a linearly independent set, and then it'll be a basis if you do either one of those. Did that make sense?
Yeah. Yeah.
So, review the spanning set theorem. But because basically it says two things. It says, if a set of vectors is linearly independent in V, then it can be expanded until it is a basis, as long as until it is a basis for B, as long as we only add more linearly independent vectors. You just got to keep them linearly independent, because as you add more vectors, the likelihood of them still being linearly independent decreases and decreases until finally you can't add any more vectors. That's your basis. Once you've got the maximal linearly independent set, it's the biggest linearly independent set that you can have. If you added any more vectors, then you would start having linear dependence. Then you stop, because once you have the maximum number of linearly independent vectors, this is an is linearly independent. Then you stop. If you have a spanning set, if a set of vectors spans V, then, well, maybe it's linearly independent, in which case, good, stop there. It spans and it's linearly independent. But maybe it's more vectors than you need. It can be trimmed to a subset that is linearly independent and still spans V. And then that would be the basis. Like you take away the vectors that you don't need because they're dependent on other vectors until you can't take away anymore. Then what you have is a spanning set that is linearly independent. Like you can't take away more vectors than span the space. Like you need a spanning set. But if you've got a bunch of vectors and they span B, you might have more vectors than you need. And it can be trimmed to a subset that is linear independent and still spans. Then you have a basis. So either way, it's two ways to build a basis, you know, because you have to have linear independence and you have to have span. You have to be able to, right? So you have to have both properties. So does that make sense?
Yeah.
Okay. So linearly independent set might not be big enough to span. You build it up, but you maintain the linearly until then it can be expanded by more linearly independent vectors. You got to keep the linear independence. I should put that in there until it's a basis. As long as oh yeah, I already said that. Yeah. Until it spans. Maybe I should say expanded until it spans V. That's better. I'm not looking at the notes. I'm just trying to pull it out of my head here.
Mm.
You expand it until it spans V, as long as we only add more linearly independent vectors, okay? So, but if it spans, it might be too big. You can trim it to a subset that's linearly independent and still spans. Okay, so you can work at it from both directions. Does that make sense?
Yeah. Yeah.
Good. And
Thank
those,
you.
go ahead.
I said thank you.
You're welcome. You ready to call it a
Mm.
night? All right.
No.
Or do
Okay,
you
we
have
can
other
go. Okay.
questions?
Mm.
Just we can, we've got a few more minutes if you wanted to look at a different.
Let's see for point four.
What?
4.4.
4.4? Okay,
Yeah.
sure. Let me get out of here. I'm trying to figure out how to go back. All right, so 4.4. Go to the assignments again. 4.4. Which number would you like to look at? Have you looked at any of those yet?
Yeah, but there is like example one you did last time in class. So like I didn't understand how you did it. So,
I'm going to pause the
um,
recording. All right, so let's look at question number 4 from section 4.4. Here we go. Let's take a peek. All right, so find the coordinate vector x beta of x relative to the given basis. So, right? All right, so obviously yours are going to be different from mine, right?
yeah,
So,
it is. It's a good number.
so section 4.4, number 4, find x beta relative to the basis that's B1, B1, B2, B3, B1, B2, B3 for the given x. All right, so B1 is, so just remember what the coordinate vector is. All right, let me help you here. Recall the coordinate vector x beta gives the weights needed to produce vector x from B1, B2, and B3. In other words, we are going to solve a, excuse me, some matrix times x beta is going to equal x. Okay, we're looking for this. These are the weights to weight the columns of P beta. But P beta is the columns that are B1, B2, B3. So you put B1 here and B2 here and B3 here. And we're looking for the x beta that gives us the vector x. So it's an augmented system, right? We're solving. This is our B now, right? So
Yeah.
we take the augmented system with B1, B2, B3, and x, and we solve it, and we get a solution. And the solution is going to tell us what the coordinates of x beta are, you know. This should turn out to be the identity matrix. And then A1, A2, and A3 actually wind up being right there. This is your x beta. All right, so you want me to do this one? Let's do this one.
Okay.
All right, so we're going to build P beta. P beta is B1 was 1, -1, 2. That's vector B1. B2 was -4, 5, 8. B3 is 2, -2, 10. And we put the x here, -9, 10, -24, okay? And so we're going to row reduce. All right, so let's put that in. Matrix 3 by 4. So 1, -4, 2, -9, -1, 5, -2, 10, and 2, 8, 10, -24. Second quit. I want to take a look at it, make sure I did it right. Second matrix. Oops. Second matrix. All right, let's just make sure that's the right matrix. All right, it is. So second quit, second matrix, math, row reduce that baby, second matrix, grab that thing. And I'm going to math frac it. Math frac. And that gives me answers in a nice form. So we get the identity matrix, and it tells us the coordinates are 7/3, 1, and -11/3. Do you know how to use math frac on your calculator?
No, I don't know like how to use the calculator. It's giving me a time.
What?
So
I didn't. So it's really easy. I had this
I
made.
have okay.
All right. So do you have, what kind of calculator do you have?
T74.
A TI 75,
74. 84.
84. So I think it's very similar. I think it's
Yeah,
very similar. If you go, all right. So
okay.
let's go. Let's quit out of this. Let's try it again. Let's clear it.
Okay.
Let's go second
Mm,
matrix. All right. So math. We're going to row reduce that matrix again. Okay, so it was that first 3 by 4 matrix. So all right. All right. So notice how this is decimals. Okay, we don't want that. Okay. So what you do is go to math. Okay.
okay.
And then there are
Um,
all kinds of menus. You can do probability, counting, different numerical stuff. But the very first option is to change
this one.
everything into fractions.
Fraction. Yeah.
So if you just hit math frac, just hit enter. And the point is,
Okay.
whatever answer you were looking at, the answer we were just looking at was a matrix answer. So it's going to take that answer and change all the numbers to fract form. Just hit enter again. And that it's like
Yeah.
magic. It changes all the answers to fractions.
Okay.
So X beta is the vector where, hey, these are the weights, 7
Yes.
thirds, 1, and -11/3. So we're solving the augmented system P beta times, this is what we're solving for. We're solving for this
Okay.
equals, we used to call this B, but we're calling it X,
Okay.
right? It used to be AX equals B, but now it's P beta, where we take B1, B2, and B3 to build P beta. The X we're solving for is now the coordinate vector, and it equals the B, is now the X. You see what I mean?
Yeah.
Because we're solving for the weights that weight this matrix's columns to build X. Let's check it. Let's check it. See, it says, hey, that the weights that we need to apply to these basis vectors to build this vector are these weights. So, we can check it. It says 7/3 times this first column, 1, 1, a -1, excuse me, 2, plus 1 times the second column, -4, 5, 8, minus 11/3 times the third column, 2, -2, 10, that these weights, these coordinates, should weight these columns to build that. Let's see if it does. All right, so we've got what? 7/3 minus 7/3, 14/3, plus, and now I'm going to change these to thirds, negative
Negative
12
12.
thirds,
Oh,
right? 15 thirds, 24 thirds, right? Plus, and I'm going to go ahead and just multiply negative 11 thirds times each one of these. This will be negative 22 thirds, positive 22 thirds, negative 110 thirds. Okay, so now we're going to add these up. 7 thirds minus 12 thirds is negative 5 thirds, minus 22 more thirds is negative 27 thirds. Hey, that is negative 9.
mm,
Negative 7 thirds plus 15 thirds is 8 thirds, plus 22 thirds is 30 thirds. Hey, that is 10. And 14 thirds plus 24 thirds is 38 thirds, minus 110. Oh, gosh. So it's negative 72 thirds. Oh, yeah, that's negative 24. So these weights, which were the coordinates of x beta, really do weight these columns to give us the vector negative 9, 10, negative 24. Does that help?
yeah.
Okay. Do you want to continue working and then maybe we could meet I can give you an extension on my math lab if you really need it, right? So if
So tomorrow morning I'm free, so I can work on it
okay, you work
in
on
the
it and then
morning.
you can
In the
email
morning.
me, if we need to meet for like, and just answer any last, any other questions, and I could always give you an extension.
Okay. Okay.
All right. I'm really tired. I gotta call it a day.
Okay. Thank you so much. Have a good night.
Thank you for asking, Anticott. I'm so glad you did. You have
Mm-hmm.
a great night.
Okay.
Bye.